In this demonstration, I'm going to develop a solution, numerical solution of radioactive decay problem, which is governed by the differential equation dy dx equals minus lambda times y, where I use the initial condition for at 0 time y was equal to 100. And this problem is going to be solved with the Euler's backward method. And in the Euler's backward method, with the Taylor series expression, we expand f of x minus h around f of x. So to first two terms, it is f of x minus h times f prime of x. We can write that one in the with the numerical indices I minus 1 to yi minus h times yi prime. And then it is simplified for the next time step from I to I plus 1. So we come across this equation yi equals yi plus 1 minus h times yi plus 1 prime. So it becomes an implicit equation. So therefore, we make a simplification that instead of using yi plus 1 prime, we first predict a value of yi plus 1 by using Euler's forward method. And then we use this predicted value to the real Euler's backward difference method. So I demonstrate its implementation in Microsoft Excel. So I have the spreadsheet, and I start with writing the cells. This is the time domain. Okay. X, which is in units of time, and I will calculate y, and I call it that it is the y predicted value, and then I will use the actual Euler's value for backward difference with the Euler's backward difference method. And I can also access the analytical solution. This is the exact solution for radioactive decay problem. And I will calculate the error here. In a programming language, we require the variable names like similar to these names. So we start our problem as 0. At 0, the computed value should be 100. This is the starting point, like the initial condition, right? And the exact value is also going to be the same 100. So let me define that one separately, that y naught value is equal to 100. So I will pick up this value from G2 from its respective cell. And I define a decay constant, which is lambda value. So for simplification, let's take that one as 1. And step size, say for the time being, 0.2. This is the expression for Euler's backward difference, and we calculate it in 2 steps. So for first step, let's define the value for a time step. So from first to second time step, it is $4. Okay. So the value has been adopted from the respective cell. Now, the first calculation, y prediction, this will be calculated by using Euler's forward method. So Euler's forward method. So the value is for y hat I wrote that one as yp in my algorithm. So this is the value I'm calling at step yp, a predicted value for yi plus 1, value at the next step, right? So it is yi plus h times f of xi by I. In our case, this is equal to the right hand side, which is the minus lambda times y value, right? So let's calculate that one. So it is equal to yi, the previous value, plus minus lambda value, which is $3 times the previous value of y, so which is here. So value of y. So this is the y predicted value times this one. Okay. And yes, it requires the h to be there, minus lambda times that one, and h should also be multiplied. So h value is $4 times the function value. So you can notice that in these parentheses, even though they are very small, in these parentheses, these are the values, right? This is the function minus lambda times y. Now, my expression has been lost, so I again use this one. Plus h times, h is $4 times the function value evaluated at the previous step. So it is minus lambda value, $3 times the previous value, which is previous value is not at B2, previous value is at C2. Yes, now the expression is correct. Now the expression is correct. So now we have a predicted value of y. We have at the current step. So now we can modify this one in the Euler's backward method. So now we can use, this is equal to yi plus h times, h is $4 times the slope value computed with the predicted value of y. So again, lambda value is at, sorry, minus lambda value, $3 times the y value at the current step, which is beside this cell. And that's it. So the value is 84. And we can repeat all that process for the next steps in time, right? This is known as a calculation in loop. So this pattern of calculation should be repeated. So we got to 3.4 time, and then, okay, so we have got several values. Earlier, I computed the forward difference method. So let's compare that one and plot all that on the same graph paper. So earlier, in the earlier demonstration, I computed the numerical result with the Euler's forward method. So let's try to make a consistent thing. H is 0.2 in the forward method, lambda was 1, started with 100. So step size 0.2. Okay, so we can compare the two. Step size is the same. So I plot the result on this same graph paper that we used earlier. So I go for the step of select data. Okay, there is the option of select data. Let me show that with the spotlight. Okay. So this is the select data. So add X values for the same time step. Okay. And Y values from the Euler's backward method expression. Calculations based on the Euler's backward method. And I will give it a name, as these are the computational based on Euler's backward difference method. Behold, it's a critical moment, the most dangerous experiment on the face of the earth. So the newly generated curve seems to appear above the analytical solution, and Euler's forward curve is below the analytical solution. So in this particular problem, it appears that the Euler's forward method slightly overestimates the results, and Euler backward method underestimates the results. So it's a great message that the two methods surround the solution. Two methods surround the solution. So this is a very successful demonstration today. Let's stop at this point. So since you have been all cool and calm and silent, so it's time to take a deep breath. It calms the mind.